When we want to design beams, all we need to do is find the required strength that we need to support and then design the beam around that. This can involve designing the geometry, choosing the material, or designing the load. We need to use the shear and moment diagrams to find the maximum moments and locations for weakness. Then we usually will look up manufacturing charts from suppliers to find the best fit, taking into account the cost, size, and the proper max strength. When we design a beam, we need to first model what the beam will be doing. If we modeled a cantilever beam like this, we would have similar trends going on independent of the geometry or material. And then the scale of the shear and moment diagrams will depend on the load. The shear diagram for a cantilever beam looks like this, and the moment looks like this. We of course want to worry about the max points, which will be the largest number, positive or negative, meaning here and here. Usually in class we will be dealing with rectangles and I-beams for beam design. Because of that, we can use some equations to help us design the factors. Remember, for I-beams we will mostly be using information provided in manufacturer charts, whereas rectangular cross-sections are common enough that they can be used with wood or any other material. Our first equation is to find the S factor for I-beams. When we want to find this, all we need to take into account is the allowable normal stress and the maximum internal moment. Then when we want to find the limiting shear stress factor, we need to find the maximum internal shear force and then divide it by the area of the web, which is usually the depth of the beam multiplied by its thickness. When it comes to rectangular cross-sections, we can simplify the equation mc over I by just using 6 times the maximum moment over b times h squared. And then for VQ over IT, for the shear stress, we can use another simplified equation, which is 1.5 V max over the area. When we are using charts to help us choose which I-beam we want in order to meet the strength requirements, there will be a lot of important information. These are the shape code, which is usually a W followed by the approximate depth, cross weight per unit length. The W means that it is wide flange beam. Depth, or D, and this is more accurate to use than the code number. Web thickness, and the S value previously mentioned. We will usually want about the XX axis because that is the strongest way for the I-beam. Knowing that info now, we need to do some of our own calculations. First, we need to find the S required, which is the maximum moment over the allowable normal stress. This means we need to know what our max moment is. Then after calculating this, we need to select a beam with an S value greater than or equal to our S required. After selecting these beams, we should choose the cheapest one, which means the least weight per unit. Then we should double check to make sure that our beam can withstand the shear stress, so we should check the allowable shear stress against the maximum shear stress over the area of the web, which is the depth multiplied by the thickness. Then if anything failed, we need to reevaluate. Now let's do an example problem with the cantilever beam that we did earlier. Since we already know that the shear and moment diagrams will look like this, I'll just give you the numbers. Since the load is 50 pounds, the max shear will also be 50 internally. Then the max moment will be at the wall, which is 200 pound-feet. Now that we know our maximum internal moment and our allowable normal stress, we should calculate our S required. Don't forget the unit conversion from feet to inches. Now that we know what our S must be, we can select a beam with the least amount of weight that meets that S required value. So we should first focus on the S column, and then find a beam that fits, like this one. But we should notice that it is a heavy beam, which means it will be expensive. Let's see if there's a cheaper one. If we look at this one, we will notice that it weighs slightly less, and it also meets the S required, so it is an overall better fit for the situation. Then we need to check the shear failure. Knowing that it must be below or equal to 17.5, by using the equation, we find that the shear stress is 6.9, and we are very safe. That means that this beam, the W2144, is our best fit.